Welcome back to Easy Academic. In this episode in the linear algebra series, we'll be discussing properties of determinants. And so if you're unfamiliar with determinants, you should consider looking at this video in the card, as it will give you an introduction to what you need to know about 2 by 2 and 3 by 3 determinants. Otherwise, first we'll start with the multiplicative property of determinants. So the multiplicative property of determinants tells us the determinant of the product of two matrices is equal to the determinant of the first matrix times the determinant of the second matrix. So say we have a matrices A and B, the determinant of this value is equal to the determinant of A times the determinant of B for any square A and B, assuming A and B have the same size. So let's show a numerical example of this. So let's say we have a matrix A, which is 2 by 2, and it's 1, 2, 3, 4. And we have a matrix B, which also must be 2 by 2. We'll set its values to 2, 0, -1, and 5. If we find the matrix product of these, we find AB is equal to 1, 3, 2, 4 times 2, -1, 0, 5. And again, if you need a refresher on matrix multiplication, you can find a link to that video in the description as well, or somewhere in the associated playlist. Find that the first entry, the first column into this matrix is equal to 2 times the first column plus -1 times the second column. And the second entry into this matrix is equal to 0 times the first column, which will be 0, plus 5 times the column 2, 4. And so we find that this is equal to 2, 6, plus -2 and -4. The second column is simply 10, 20. And this in sum is equal to 0, -2, 10, 20. Sorry, 0, 2, 10, 20. So if we take the determinant of this, we'd be taking the determinant of 0, 10, 2, 20. And this gives us 0 times 20 minus 10 times 2, which is -20. However, if we took the determinant of A, which is the determinant of 1, 2, 3, 4, and from this we get 1 times 4 minus 2 times 3, we get 4 minus 6, which is -2. If we then take the determinant of B, which is equal to the determinant of 2, 0, -1, 5, we'd find that we have 2 times 5 minus 0 times -1. And there we get 10. So, the determinant of A times the determinant of B, and remember, the determinant gives us two scalar quantities, is -2 times 10. Which is equal to -20, which you'll observe is the same as the determinant of A times B. The second important property to show is the transpose property. So quite simply, all this says is that the determinant of A is equal to the determinant of A transpose. So again, let's take a simple 2 by 2 matrix, 1, 2, 3, 4, and find its determinant. So the determinant of 1, 2, 3, 4 is equal to 1 times 4 minus 2 times 3. For this, we get 4 minus 6, we get negative 2. If we then take A transpose, swapping the rows and the columns, we get 1, 2 as the first column, and 3, 4 as the second column. So if we take the determinant of A transpose, we obtain the determinant of 1, 3, 2, 4. And we get, again, 1 times 4 minus 3 times 2, which we'll observe again is 4 minus 6, which is negative 2. Lastly, I'd like to show the effects of the row operations that we use in Gaussian elimination on the determinant. So first, what happens when we swap rows? Swapping rows gives your determinant the inverse value. So say, for example, you have the matrix A, which is equal to 1, 2, 3, 4. If we swapped row 2 and row 1, so if we swapped these two rows to give us this new matrix A prime, which is equal to 3, 4, 1, 2, the determinant of A would be equal to negative the determinant of A prime. And so let's show this. We know the determinant of A to be negative 2 from the earlier example here. So let's compute the determinant of A prime. So the determinant of A prime is equal to the determinant of 3, 4, 1, 2, which is equal to 3 times 2 minus 4 times 1. From this, we get 6 minus 4, which is equal to 2. Now, as you'll observe, 2 is a negative of negative 2. So what happens if we scale any given row I by some value, let's call it k. So if we scale a row I by a constant k, we multiply the whole determinant by k. Let's take our original example of 1, 2, 3, 4. And transform its second row by multiplying it by 3, which will give us the new matrix A prime, which is equal to 1, 2, 9, 12. We know the determinant of this to be equal to negative 2. But if we now took the determinant of A prime, we'd find we're taking the determinant of 1, 2, 9, 12, which gives us 1 times 12 minus 2 times 9. This gives us 12 minus 18, which is equal to negative 6. And we know that negative 2 equals some value k times negative 6. We know that negative 2 times k equals negative 6. And pretty intuitively, you can tell that k equals 3. Finally, what happens if we add a scalar multiple of one row to another? Well, in this case, the determinant doesn't change. So if we have, again, our matrix A equal to 1, 2, 3, 4, and say we add 2 times the first row to the second row, which would give us 1, 2, and then 2 times the first row, so 5, and then 8, we'd get the exact same determinant as the determinant of A. Now this may seem a bit unintuitive, but let's show it with this example. So we know that the determinant of A is negative 2. If this is A prime, we show that the determinant of A prime, which is equal to the determinant of 1, 2, 5, 8, is equal to 1 times 8 minus 2 times 5. This is equal to 8 minus 10, which is negative 2. So as you can see, the determinants of A equals the determinant of A prime. And so to recap, the effects of the 3 row operations are as follows. Swapping 2 rows multiplies your determinant by negative 1. So if you have a matrix A, if you've obtained its determinant and then swap 2 rows, the determinant of the new matrix is negative 1 times the original matrix. If you scale any row I by some value k, you scale the determinant of that matrix by k. And if you add any row, or any scalar multiple of any row, to any other row, it has no change on the determinant. And so these are the properties of determinants in matrices. Feel free to comment if you have any questions on the concept below. Otherwise, if you found this concept useful, please like the video and subscribe to the channel.